Welcome back to 3 Inquisitive Kids. In this video, we will be solving multiple problems on finding the range of functions. And through these examples, we'll get used to 4 main methods on how to find the range of a function. Here are the 4 ways. We have monotonocity, the discriminant, substitution method for roots, and the final method is about connecting algebra with geometry. Here's our first problem. We're going to find the range of the function x plus 2 squared over x squared plus 4x plus 5. So let's start off by expanding this a little bit. F of x is equal to x squared plus 4x plus 4 over x squared plus 4x plus 5. We just expanded the numerator. Now, the numerator and the denominator are very similar. They're only apart by 1. So we can rewrite this whole thing as 1 minus 1 over the denominator. Let's pause and think about why we can do this. Well, we kind of just turned the numerator into the denominator minus 1. That's all we did. And the denominator can be rewritten as a perfect square plus 1. So here is our new version of the function f of x, and we're told to find the range of this. Now let's kind of think about the monotonocity of the function. This is when we're basically trying to think about, on a certain interval, is the function increasing? Is f of x increasing along with x? Or is it decreasing as x increases? So here we have a perfect square. Perfect squares can only be 0 or more. So x plus 2 squared has to be greater or equal to 0. And when we add a 1 to it, this is the full denominator, we know that the denominator has to be greater or equal to 1. This means that the denominator can go from 1 all the way up into infinity. As the denominator gets larger and larger, all the way into infinity, the entire fraction becomes closer and closer to 0. So we're basically subtracting a value that's getting as closer and closer to 0 from 1. But this approaches 0. It doesn't actually get to 0. So we never end up with f of x is equal to 1 minus 0. So f of x is always going to be slightly less than 1. It's going to approach 1, but it's never going to actually get to 1. And we know that if the denominator of the fraction is 1, we get 1 minus 1 over 1, and that gives us 0. So f of x can equal 0. This tells us the range of the function. Now we know that f of x goes from 0 inclusive up to 1. So we just solved this problem using the monotonocity method. But there's another way we can do this. We can use what we call the discriminant method. Let's replace f of x with y. And now we're going to multiply the denominator on both sides of the equation. We're also going to expand the x plus 2 squared. Now, let's combine terms to get ourselves a quadratic that is about the variable x. As you can see, now we have a quadratic equal to 0, and we have the variable y in each of the coefficients of the terms. So now we can use the discriminant. The discriminant, if you don't remember, is basically b squared minus 4ac. This is part of the quadratic formula. It's the part under the square root of the quadratic formula. So in order for a quadratic to have a solution, basically in order for x to have some real values to make this equation true, the discriminant must be greater or equal to 0. And here, the B, the A, and the C we're talking about is referring to this form. So in this case, B, which is the coefficient of our x term, is equal to 4y minus 4, minus 4 times A times C. This must be greater or equal to 0. Now we can simplify. We see that now we have an inequality with only the variable y. And this is exactly what we want because we're trying to find the limits of what y can equal. So let's expand our expressions. We can divide both sides of the equation by 4. Now we can further combine like terms. We're left with negative y squared plus y must be greater or equal to 0. We can divide both sides by a negative 1 if we want. From this, we can factor to get y times y minus 1 must be less or equal to 0. So first, what values of y makes it 0? If y itself is equal to 0, this inequality holds true. And if y is equal to 1, this inequality also holds true. And if we have something in the middle, like let's say 1/2, this is also holds true. If we test something in this interval from 0 into negative infinity, let's say negative 1, this does not work for our inequality. And let's test a value from this interval. Let's do 2. 2 times 1 is positive. That does not work for our inequality. So it seems like the only possible values for y is from 0 to positive 1. But here's the catch. Y cannot equal 1. We need to remind ourselves this. We actually should have done this earlier. It's because when we go back to our original quadratic, if y is equal to 1, then we are left with 5y minus 4 is equal to 0. And if we solve this, y is equal to 4 over 5. Y cannot equal 1 and 4 over 5 at the same time, which means that y can only go from 0 to 1, but not inclusive. So this is the range of our function. As you can see, we ended up with the same answer as the previous solution. Our next problem is to find the range of this function, the monotonocity method. This is when we're analyzing whether a function is increasing or decreasing for certain values of x. So let's break this down into parts. We have y is equal to x minus 1 minus 7 minus x in a square root. Let's first find the domain. This way we can analyze what x values we're dealing with. We know that the section under the square root definitely has to be greater or equal to 0. So x must be less or equal to 7. This means that the domain goes from negative infinity to positive 7 inclusive. If we look at this first half of the function, x minus 1. As x increases, x minus 1 also increases. So it has a monotonicity of increasing. Now what about the second half of our equation? For the square root, as x increases, the square root's value decreases. So as x's value increases, we're subtracting less and less from the first half of the function. Which means that overall, as x increases, y increases. And since we already know the domain for the values of x, we can just use what we know. When x is all the way into negative infinity, y will also be really, really small, negative infinity. But when x is at its maximum value, which is 7, y will also be at its maximum value. So we have f of 7 is equal to 7 minus 1 minus square root of 7 minus 7. This is equal to 6. This tells us that the range goes from negative infinity to 6 inclusive. And this is the range of our function. Now let's find the range of this function. Y equals x minus 1 plus the square root of 3 minus x. This is very similar to the problem we just did, except now we have a plus sign between the first and second halves of the function, and the 7 turned into a 3. First, let's find our domain. It's always a good habit to start with this step. 3 minus x must be greater or equal to 0, which means that x must be less or equal to 3. So the domain goes from negative infinity to positive 3 inclusive. Now let's jump right into our problem. When we see a square root like this, it can turn very confusing as we go on. One method is to use what we call the root substitution method. This is when we take another variable, let's say t, and use it to substitute for a square root. Let's let t equal to 3 minus x in a square root. We can also let x minus 1 be represented in terms of t. We know that t is equal to square root of 3 minus x. So then t squared must be equal to 3 minus x. And then negative t squared must be equal to x minus 3. And if we add 2 to both sides, this would give us x minus 1. So we can let 2 minus t squared equal x minus 1. So then the function y would be rewritten as t plus 2 minus t squared. Now, this is in a form of a quadratic that we're very familiar with. Y is equal to negative t squared plus t plus 2. So we know that the graph of a quadratic is a parabola. And when we have a negative coefficient in front of the t squared term, we know the parabola is opening down. So this is what our parabola might look like. And it's symmetrical about a vertical line that goes through its vertex. And this vertex should be the highest point of the parabola. The vertex has an x value of negative b over 2a, and this is referring to ax squared plus bx plus c. This is the standard form of a quadratic. So in this case, the x value of our vertex would be equal to 1/2. And now all we have to do is find the y value of the vertex. Well, we can substitute t equals 1/2 into our quadratic. So y would equal 1/2 plus 2 minus 1/2 squared, which is 1/4. This is equal to 9/4. So the y value of our vertex is 9/4. And 9/4 is the highest our y value is ever going to get. Because from the vertex in onwards, on both sides, it just keeps going down into negative infinity. So the range of our function, which is all the possible y values, is just negative infinity to 9/4 inclusive. And that's how we solve this problem. As you can see, we used the root substitution method to make what seemed pretty complicated and random to turn it into a form that we're very familiar with. And then we used a drawing, a visual representation, to help us better understand. We're going to find the maximum value of y equals the square root of x plus 6 plus the square root of 8 minus x. Let's start off by finding our domain. X plus 6 must be greater or equal to 0, and 8 minus x must be greater or equal to 0. Solving for x must be greater or equal to negative 6, and x must be less or equal to positive 8, which means that our domain goes from negative 6 to 8 inclusive. So now let's apply what we used in the previous question To solve, we can use the root substitution method. Let t equal the square root of x plus 6. And the square root of 8 minus x, if we want to represent it in terms of t, would be equal to t times the square root of 14. Now, y can be rewritten as t plus t times the square root of 14. So how can we make t plus t times square root of 14 as large as possible? Well, if we directly take x's largest value, x equals 8, t would be equal to square root of 14. But then this whole part, t times square root of 14, would just be equal to 0. So it's kind of wasted. Now, on the other hand, what if we had the least value of x? In this case, t would be equal to 0, and t times the square root of 14 would be equal to square root of 14. So in both scenarios, we have y is equal to square root of 14, which means that y equal to t plus t square root of 14 is kind of symmetrical. So what if we find a value of x right between -6 and 8, right in the middle, that might lead us to a y value that is of the largest? So what would that value be? Well, we can have positive 1. 1 is equidistant to -6 and positive 8. So let's see what happens when x is equal to 1. T would be equal to square root of 7, while t times square root of 14 would be equal to square root of 7. When we add this together, we get 2 times the square root of 7. Let's see if this is larger than the other two values we got. In fact, it is, because when you square all of these values, we can see that 2 times the square root of 7 gives us the largest. So the maximum value of this function is y is equal to 2 times the square root of 7 when x is equal to 1. And the thing is here, before we answer a question like this, we have to double check that x, this value of x, is actually part of the domain. Because if the domain did not cover 1 in the first place, then this answer we had would also be counted as wrong. Now we're on to our next example. We're going to find the maximum value of a function again. We have 2 square roots being added together. And these square roots, we could try to represent them using the same variable, but it's still going to be a little bit complicated. So why not we just substitute them using 2 different variables? Let a be equal to square root of 3x plus 6, and b be equal to square root of 8 minus x. And we're going to tell ourselves that a and b must be greater or equal to 0, because they're square roots. Now, when we take a squared, it's equal to 3x plus 6, and b squared is equal to 8 minus x. Now we just got rid of the square root symbols, which is great. Now, how can we find a way to combine a squared and b squared and be left with some sort of constant? So we can add them together, but first we can multiply a 3 to b squared. This way, we're doing essentially 3x plus 6 plus 24 minus 3x, which gives us 30. Well, that's easy. Y is equal to a plus b. Here are 2 our equations. And in the end, we're actually just trying to solve for y anyway. So let's try to get rid of one of the variables, a or b. So we can let a be rewritten as b minus y, and then substitute it back into this equation. We have b minus y squared plus 3b squared minus 30 is equal to 0. And hang on tight, because we're going to turn this into a quadratic. We have b squared minus 2by plus y squared plus 3b squared minus 30 is equal to 0. We're about to use the discriminant method for finding the maximum value of the function y, which means that we're going to try to turn this quadratic into a quadratic that is about the variable b. This way we can get all of the y's into the coefficients of the terms. So we have a 4b squared minus 2yb plus y squared minus 30. And this is equal to 0. Now let's apply the discriminant. We know that 4y squared minus 4 times 4 times y squared minus 30 must be greater or equal to 0. We can divide 4 on both sides to get y squared. This is equal to negative 3y squared plus 120 is greater or equal to 0. Now we know that y must be the square root of 40, which is 2 times the square root of 10. Now we have the upper bound for the values of y, but what's the lower bound? Well, the lower bound would just be greater than 0. Well, how do we know this? It's because when we go back and analyze our original expression, we see that y is the sum of 2 square roots added together. And since square roots must be non-negative, y's value must be positive, or if these 2 square roots are both 0, then 0. But clearly, if we test it, there's no x value that makes both of these square roots 0 at the same time. So y is just positive. It cannot equal 0. That's how we know it has a lower bound of 0, not inclusive. So let's double check to see if 2 times the square root of 10 is indeed a maximum value of y, because we need to find if there is an x value that could produce 2 times the square root of 10. We forgot to do the domain. Let's do the domain of the function. 3x plus 6 must be greater or equal to 0, and 8 minus x must be greater or equal to 0. So the domain must go from negative 2 to positive 8 inclusive. So remember the quadratic we had here? We're going to substitute y is equal to 2 times the square root of 10 in here and see what we get for b. Now we're going to use the quadratic formula. This gives us b is equal to square root of 10 over 2. And what is b in the first place? B was equal to square root of 8 minus x. So this should be equal to square root of 8 minus x. And now let's solve for x. So we find that x is equal to 11 over 2, which means that when x is equal to 11 over 2, y is equal to 2 times the square root of 10. And let's see if 11 over 2 is part of the domain. It is indeed between negative 2 and 8, which means that our maximum value for y does work out. It does exist. So for this problem, we use the methods of root substitution as well as the discriminant method to find the maximum value of y. Now let's find the maximum value of this function. We can see we have one square root being subtracted from another. And we see that the parts under the square root looks like they can be factored further. So why not we kind of factor the inside of the square root first? This would be equal to, now we can see that we have a common factor of 8 minus x under each square root. So why not we factor out that 8 minus x? We're left with the square root of 8 minus x times the square root of x minus the square root of x minus 6. So now let's analyze using monotonicity. We can see that as x increases, this part decreases. So this entire square root's value would decrease. And what about our parentheses? As x increases, the value of square root of x would increase, and then the value of x minus 6 will also increase. But the square root of x minus 6 will always be less than the square root of x, because x minus 6 would always be less than x. So as x increases, this entire value will start to decrease. But now we have to remember that even though these two parts are decreasing, they're always going to be positive, because square roots cannot be negative, and they're not going to be 0 in this case. So we can use another math trick, which is called rationalizing the denominator when we're dealing with square roots. Y is equal to, we're going to use a square difference formula. Now we can rewrite. The numerator of this fraction is just 6. So now we can analyze. Again, this part, as x increases, decreases, but it stays positive. As x increases, the denominator here also increases. But if the denominator of a fraction increases, it means the entire fraction itself decreases. It means that as x increases, y in general decreases in the long term. Which means if we want y to get larger and larger to reach its maximum, x must be decreased to its smallest possible value. So now, what is the smallest possible value of x? Well, that just means we need to find the domain of x. We know that all parts under the square root sign must be greater or equal to 0. I want you to pause the video right now and see if you can find the domain of x. So after simplifying, you should get that the domain goes from 6 to positive 8, inclusive. So the smallest possible value x can be is 6. Now let's substitute 6 into our function. Y would be equal to the square root of 2 times 6 over the square root of 6 plus 0. This is equal to 6 times the square root of 2 over the square root of 6, which is equal to 2 times the square root of 3. So our answer is the maximum value of y is 2 times the square root of 3 when x equals 6. Here's our next example. This is going to be a fun one. We're told to find the range of f of x and the sum of two square roots. We can see there's a quadratic inside of each square root, and they look kind of different from each other. So our first step, let's try to factor and see what we find. X squared plus 2x plus 5 cannot be really cleanly factored by itself, but we can split it up. It's equal to 6 plus 1 squared plus 4. And what about our next quadratic? That is equal to x minus 2 squared plus 4. So it seems like we have a plus 4 under each of these square roots. When we see something in the format of this, what do we think of? Well, this reminds us of the distance formula between 2 points. We can kind of transform this a little bit. Some geometry will be involved in solving this problem. 4 is equal to 0 minus 2 squared. Now if we try to look at this from a geometric or visual perspective, we can tell that this first radical symbol is representing the distance between 2 points. And these 2 points are x, 0 and -1, 2. And our second square root symbol is representing the distance between x, 0 and 2, 2. Let's try to graph this out. This way we can better visualize it. Let's call -1, 2 point A, and let's call 2, 2 B. Now, the range of f of x just means that we have to find the smallest possible sum of these two distances and the largest possible sum of these two distances. x0 is any point along the x-axis. So what would be the maximum value of f of x? Well, x could just keep going way into infinity to the right, or go all the way to infinity in the left. So the maximum possible value of f of x is just positive infinity, because the distance between x and a and x and b added together can just equal infinity. So what we're really trying to find here is the smallest possible value of these two distances combined. So a way to solve this problem is taking one of these points, a or b, and then reflecting it over the x-axis. So let's reflect b into b prime. We know that a straight line is always the fastest or the shortest distance. Now we're going to connect a and b prime. This distance is the same distance as if you go from a to x and then x to b. Where ab prime intersects the x-axis is where point P is. So the coordinates of A is -1, 2, and the coordinates of B prime is 2, -2. So AB, what would its equation be? Its slope would be -4/3, and let's find its y-intercept. Its y-intercept is equal to 2/3. So now let's find where this line AB prime intersects the x-intercept. AB prime intersects the x-axis at the point 1/2, 0. This means that the minimum value of these two distances combined, in other words, f of x, is found when x equals 1/2. So now let's substitute x equals 1/2 back into our original f of x function. So let's substitute it in here. We have +5 as our answer, which means that the minimum value of f of x is +5. So that is the range of our function. Here's our last problem. We're going to try to find the minimum value of this function, and this function is a function of two variables. So this is very similar to the previous problem. We're going to try to turn this into a geometric problem, what we know as the distance formula between 2 points. So let's factor. The first radical symbol is equal to the square root of x minus 1 squared plus 0 minus y squared. When we're factoring and trying to create two perfect squares in here, we're going to try to make one of the coordinates in a point 0. This just makes it easier to move around. We know that a point must lie on the x or y axis somewhere. So now we have our factored forms. And you might ask, well, why did you specifically factor the last quadratic inside to look like this? It looks kind of indirect. Well, I factored it like this. For example, having a y minus 5 and then having a y minus 3, because we want to try to work with as less different variables as possible. So I kind of tried to create the same point that will appear multiple times. So the first radical represents the distance between 2 points, x, 0 and y, 1, y. I factored these three radicals specifically so that we would have the same points appear multiple times, like 1, y and x, 0. And the other points are just fixed points. Now Now let's graph this out and see what it looks like on the coordinate plane. 1, y would lie along this vertical line where x equals 1. 5, 1, we'll make it here. 5, 3, we'll make it here. And x, 0 is just sliding along the x-axis. Now we're trying to find the minimum value of these three radicals combined, which means what is the smallest possible length of the length of these three line segments combined. In order to stay organized, let's name these points. So 5, 3 can be called A, and 5, 1 can be called B. And x, 0 can be called P, and 1, y can be called Q. Basically, we're trying to find the distance between P and Q, P and B, and A and Q. So we can do some flipping about the axes too, like we did in the previous video, to use what we know about a straight line is the fastest, or a straight line is the shortest. So let's reflect A about the line x equals 1. Now we have a new point called A prime, and its coordinates are -3, +3. We can also reflect B over the x-axis, and its coordinates would be 5, -1. Originally, we were trying to find the distance between AQ plus QP plus BP. But now, all we're trying to find is the distance between A prime Q plus QP plus PB prime. Q and P are movable. That's why it means we're actually trying to create them. So under what circumstances would the sum be at its smallest? Well, it would be at its smallest when we have a straight line, because straight lines are always the shortest. Q would be here. It's where the straight line A prime B prime intersects the line x equals 1. P would be here. It's where the line segment A prime B prime intersects the x-axis. Now all we have to do is find the equation of A prime B prime. Its slope is 1/2. And what is its y-intercept? Let's find that out. Its y-intercept is equal to 3/2. Now we have the equation for A prime B prime. Now we can see where it intersects x equals 1. When x equals 1, its y-coordinate is 1. And this might not match what I drew in the graph, but that's just because my drawing was not accurate. But we have abstract mathematical minds, so it's acceptable. Where does this intersect the y-axis? We see that x must equal 3, which means that P has coordinates of 3, 0. And going back to our original function, we see that in place of x, we have 3. So x equals 3 now. And in place of y, we have a 1. So y equals 1. So now we have the values that will make our function at its minimum. Now we just have to substitute these values back into our function. So let's substitute it in here. We're left with the minimum value of f of x, actually it's not f of x, it's f of x, y, is equal to 4 times the square root of 5. So this is our answer. Now let's do a recap of what we learned in this lesson. In this lesson, we learned how to find the range or the maximum or minimum values of a function, whether it's about one variable or two variables, using 4 different methods. The first method is analyzing its monotonicity. Monotonicity is analyzing, well, when x increases, does the output y also increase or does it decrease? And we also use the method of the discriminant. This is when we took y, because y, aka f of x, was the variable we're trying to find a bound on, which means we're trying to put an inequality on the y. So in order to do that, we kind of constructed ourselves a quadratic and then put y into the coefficients of those quadratics. and then we use the discriminant to end up with an inequality only with the y variable in it. Another method we used was the root substitution method. When we saw a square root, we just called it some other variable, let's say t, and oftentimes this would simplify the format of our function. And then the fourth way we used was the geometry algebra combination method. It means we're turning an algebraic problem into a visual geometric problem. This way, we can also use some of our geometric skills to help us solve the problem. I hope you learned something from this video, and I'll see you in the next one.